Welcome to week 6 of MLF. And today we'll be talking about probabilistic models. So here's a quick content for today. We'll first talk about what is a probabilistic model, and then we'll talk about maximum likelihood estimation, which is MLE in short. And then we'll talk about discriminative and generative models for kind of classification problems, but actually can be applied to all the problems. And then in the end, we'll talk about Bayesian models. So yeah, today's content is going to be hard, and then it will be very fast paced. So hopefully everyone will be follow along, but definitely ask questions if you have any. So yeah. Okay, so let's talk about what is probabilistic models. So these are stuffs you've seen before, right? Linear regression, logistic regression, neural network, and decision tree. So that's what you learn the first 5 weeks. Yeah. So what commonalities does those things have? And like those models have in common? Yeah.
You need to train it with data.
Well, machine learning, you always need data to train a model. Yeah. But it is a commonality, but
They are deterministic.
yeah, they are. Yeah, that's the answer. So yeah, if you know, what you've seen so far, they're all deterministic models. So what deterministic model is, so let's say I have some sort of model, right? And then I give it an image of a cat, and then it tells me it's a cat with like, let's say 90% probability of it being a cat. And then if you give this the same model, the same image again, it will give you the same results. So it will predict it's also 90% cat, right? So basically, in simple terms, deterministic model just means that if you have the same input and then same model, it will always gives you the same output, right? And this can be defined as like mathematically, let's say if you have an input X and your model F of theta, and then your output is Y pred, which just equals to F of theta of X. And this just means you're passing in the input to the model and you get an output. And then your prediction of the prediction being Y pred is always 1, right? So you're always 100% that your prediction is going to be the same. Does that make sense? Yeah, so that's deterministic model. So by deterministic model, they're fast and reliable, right? And they're really transparent and interpretable because you don't have to worry about like it giving different results. So imagine you have like a piece of code, right? It's just like a function or something. Then let's assume that your function doesn't involve using any like random numbers or stuff. Then you expect your like giving the function, passing in the call the function with the same input, you always get the same output, right? Like you don't want to call the same function with the same input and then get like a different output every single time. That would be very bad. So that's why we use deterministic model. But well, I think everyone knows that everything in our world is definitely not 100% deterministic, right? So just as an example, I gives you the temperature and humidity today. Can you predict like what the weather is tomorrow with 100% confidence? Probably can't, right? I mean, you can say, oh, like today is raining, so I predict tomorrow's also going to be raining, maybe, but you're never 100% sure of something. So like it's kind of like you're predicting a probability, like I'm 70% sure tomorrow's going to rain, right? That's also what weather forecasts do. Like it's not always 100% accurate. So why we have this phenomenon is because our world involves uncertainty. And there are two types of uncertainty. So the first one is called aleatoric uncertainty. So it's uncertainty within the data. So it means just the world is noisy by itself. And there's also epistemic uncertainty. So epistemic uncertainty means the uncertainty from the model. So it means your model haven't learned something or haven't seen something. So I'll give like 2 examples for each, like 1 example for each. So if you don't fully get it, that's okay right now. But just know that this is key, that aleatoric uncertainty is inherited from the role. So you can't really like reduce it. Like there's no way you can reduce it to 0 or something. So pretty much there's not too much thing you can do about it. And epistemic uncertainty, on the other hand, is due to the model's knowledge problem. So it can be reduced by collecting more data or stuff. So epistemic uncertainty, ideally, you could reduce it to 0, but of course, in reality, you couldn't really. So here's an example for aleatoric uncertainty, right? So if I give you like a very, very blurry image, it's like you can't really see anything from it. Let's say it's just completely white or black. Then even if you have like a perfect model that can predict whether, let's just say, a given image is cat or not, you can't really, like, model doesn't know, right? Or it's just very blurry that you can't really tell anything from it. So there's nothing you can do about it because the issue is just the data itself, or it's like where the data comes from, which is the role. So it's just noisy itself. And for epistemic uncertainty, on the other hand, let's say if you have a model that's only trained on this, like telling if it's a cat, but it's only trained on whether the cat, like, it's only trained on image of black cats, actually. So it will be uncertain when it sees an image of white cat, right? But this can be solved easily. You can just say, let's collect 100 images of white cats, and then let's keep training the model on those. And then after training, your model would be, oh, I know that this is like a white cat now, so it's a cat, right? Yeah. So in reality, your prediction always lies on like in between the two, which there's always some epistemic uncertainty and aleatoric uncertainty, but in the end, epistemic is what you're like mainly dealing with because there's nothing you can do with aleatoric uncertainty. So now let's talk about probabilistic model. So probabilistic models take into account of uncertainty, which deterministic model, of course, does not. And this is done by maintaining a probability distribution of some form, whether explicitly or implicitly within the model or as the output. And the probabilistic model kind of represents your understanding of the event. So I guess we'll see more of that, what it actually like kind of means. But just remember, it's kind of representing your knowledge of the event. And formally, mathematically, you have an input of x, which is your data. And then you have some sort of model, f of theta, right? So your model kind of is built as a distribution parameterized by theta. Actually, I think the notation is not 100% correct. The model should be just theta itself instead of f of theta. But you can just think of your model as being parameterized by theta, and then it maintains a probability distribution of given y, which is your label. Oh, given your data and model, how likely would it be to have a prediction as y? And when you're doing output, all you do is just use samples from that probability distribution. And so what you get is just y pred, and then you samples from it. So yeah. But the key here is just you maintain some sort of internal probabilistic distribution within your model, which your deterministic model does not, because it's just purely passing through numbers through layers. Okay. So here's a very common misconceptions. So having probability in your model doesn't mean your model is probabilistic. Okay. So the key characteristic for a probabilistic model is that it maintains some sort of probabilistic distribution and they use it. And of course, for some cases, that's really dependent, but for most probabilistic model, given the same input, you don't get the same output every single time. So let's say ChatGPT, right? If you give it the same prompt, which is the same question again and again, you would probably get like something very similar, but that's not the exact same answer, right? So that's why you have you can consider GPT as a sort of probabilistic model. And the third key characteristics is what distinguished a true probabilistic model than a like normal probabilist. So the definition here is kind of like blurry. Depend on how you want to define the model. But for true probabilistic model, which are Bayesian model we'll talk about in the end, your parameters are actually treated as random variables. So each parameter, instead of being fixed, is treated as some sort of distribution as well. But for deterministic model, for what you've seen so far, all the weights or all the parameters are just like a fixed number or something, right? And that's not the case for probabilistic models. Yeah, and well, logistic regression, you can think of it like as a probabilistic model according to this definition, because technically it uses the distribution for the output, right? So it uses Bernoulli distributions for binary classification, but I personally don't consider it to be a true probabilistic model because there's nothing probabilistic about it other than output's probability, right? Yeah. Does that make sense so far? Okay, good. Yeah, so now let's talk about maximum likelihood estimation, which is MLE for short. So you're probably familiar with the term probability, right? And you may also heard the term of likelihood. So in most cases, actually, people just treated them as the same thing, but they're actually not. So let's give them like more rigid definition for each of them. So probability just means given a fixed model theta, right? What data would we observed? And then in the formula, it's just probability of D given theta, and then theta is your model, and D is your data. So I'll have an example in the next slide. But just for now, remember probability is that given model, given a fixed model, so your model is fixed. Here your theta is fixed. And then what's the probability if you observe some sort of data? So it's always from model to data. And likelihood, on the other hand, is given some sort of data, what model produces it? So you see the formula is like, it looks exactly like the probability, but here what's being fixed is different. So for the top formula here, yeah, so this theta term is fixed, right? And for likelihood, however, you can think of likelihood as being a function of theta. So your theta is constantly changing. And then so you will get different L as a result. So likelihood in short is from data to model.
What is theta?
Theta is just your model. It can be like any machine learning model or whatever.
Output of the.
Yeah, you can think of it as like kind of output of the model, but
D.
D is your data. So like let's say you have a data set, right? So then D is just your data set. Let's say you have like a data set, right? Then D is just your data set. Like that's your data.
Probability of data set. What is it? What's the probability?
For which one? The first one is just like it gives you a model theta, right? And theta is being fixed. How likely would it produce those kind of data, basically? Does that make sense? I have like an example in the next slide, so maybe you can go to that. So for probability, let's say I gives you a fair coin, and then fair coin in this case is just your model, right? So it flips, like it generates heads 50% of the time and then tails the other 50% of the time, right? So then your probability is just that given this model, which is a fixed coin, how likely would it, right, generate a head, which is head is in this case just your data. So how likely would it be to generate some sort of data? And then getting a head given a fair coin is just 0.5, right? That's pretty intuitive. So likelihood, on the other hand, means that if we observe the data, we observe some sort of sequence of data, right? Which is head, 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 tail, head in this case, then what's the probability of model that produces this kind of data? So you see the difference here is that for probability, you know what the model, right? And then you try to recover whatever the data is. And then you try to figure out how likely is this model generating the data. So it's always from model to data. But for likelihood is that you observe the data first. and then you try to figure out what sort of model generates this. So it's always given data, likelihood always goes from data to model, where probability goes from model to data. So it's kind of inverse.
Here maybe data is the fair coin that returns.
Yeah, so
times over 5 head.
Yeah, so in this case, like to your data, I mean, it can be anything, right? It can be like a coin that always lands on tail, and then you see how likely would it. So likelihood is that given the coin always lands on tail 100% of the time, then how likely would it generate this data? And then it's 0, right? Because there's no way if a coin always lands on tail and then generate this sort of data. And then similarly, if you have a coin that lands on head, like has a higher probability of landing on heads than tail, then it's more likely to generate this kind of data, which you see has more than like a fair coin. If that makes sense. But here, like for likelihood, your objective is just try to find the best model that gives the highest chance of producing the data. If that makes sense. So those are kind of inverse, right? So probability is you know what the model is, and then you try to recover the data. Where likelihood is that given this sort of data, you try to figure out what's the best model, or what's the potential model that generates this. Yeah. Does that make sense to everyone? Yeah.
Given a model, likelihood is likelihood of that model generating data.
Yeah, but for likelihood, you are not fixing the model. You are trying to figure out which model given that generates this data. So for probability, again, you know the fairest coin was 100% sure, right? But the coin's fair with 100% certainty, right? Right. But for likelihood, you're not sure about that. So you can say the model can be like a coin that always lands on tail, or it can be a coin that always lands on head. It can be anything. So as I said, it's a function of theta. So your model can be changing, and then your goal is to find the best model that kind of generates the data you see. Yeah. So remember, just like if you don't truly understand, just remember for probability, your model is fixed. So this term, you know what your model is. So you know the coin is fair or it's biased, but you know it with 100% certainty. For likelihood is you only know the data. And then you try to construct a model to understand how this data is being generated. So yeah, those are two kind of the reverse thing. Okay. So some properties of likelihood. So likelihood has the following property. First of all, it's non-negative. So because as we said here, right, it's just a probability. Like it's not really truly a probability, but it's equals to a probability of some form. So according to the rule of probability, it can all like it's just between 0 and 1, right? So yeah, your likelihood can only be non-negative. And then there's something called relative plausibility. So that's how we compare two models. So let's say if I have like likelihood, given the same sort of data D, and then you have two models, theta 1 and theta 2. And then if the likelihood for D of theta 1 is greater than the likelihood of seeing D given theta 2, then we say theta 1 fits the data better. So you can like, not really like with 100% certainty, but based on what you have, you can say theta 1 is a better model than theta 2 because it gives a higher probability of seeing this data, like based on the data you have, because data is all you have, right? That makes sense. Yeah, and then with the data is discrete, your likelihood can take on value less than 0, can only take on value between 0 and 1. And then for continuous case, it can take like greater than 1. It's just PDF and PMF, but it doesn't really matter. But if you're
Why we can have values greater?
If it's continuous, because continuous your PMF is your PDF is a function, right? And then it only requires you integrate from negative infinity to infinity to be 1. That's more of probability stuff. It doesn't matter here.
Oh.
Like I just like put it there in case you're interested, but like it won't affect anything we're talking about later. But yeah, like for the PD, for continuous case, it only requires you to have a integration over 0. So you can have some point being greater than 1. So now let's talk about maximum likelihood. So our objective here is for likelihood is to find the best sort of model that generates the data or that produces the data, right? And then once you have a model, you can do anything with it, like making the next prediction, or you can generate some sort of new data, which we'll see later. But formally, you can formulate this objective of being theta hat MLE, and then theta hat MLE is just your best model. So it's a model where you can think of it as like you're trying to figure out how biased the coin is, and then you're trying to figure out what's the best coin that generates some sort of data you observed, right? So how you define this is just the argmax of theta of p given p of d given theta. So all it means is just for all the possible theta, you're trying to find that one that gives you the highest likelihood.
What is R?
Hmm?
R.
Argmax.
Max.
It's just depending on, like, you're picking the theta instead of the actual number. So like if I put without the arc here, max of p d given theta would just be the number, right, of highest p. But argmax, we're picking the theta.
Arc is for arc.
Yeah, we're picking out this like highest. No, we're picking out the theta that gives the highest number for p of d given theta. So we're picking out the argument. We're picking out this term instead of the actual like numerical value of this term. If that makes sense. Yeah. So all in all here, like all you do is just try to find the best possible model. So like that's what we're doing here. And usually the data points are considered independent. So you can multiply the likelihood together. So what it means is that let's say you have a coin, right? You flip it first time, you see heads. Then you try to flip it a second time. Whether you see a head or tail on the second flip doesn't matter with your first flip, right? So like that's what it calls independent. So every single event in the experiment is independent. Like, yeah, every single event is independent from each other. So like no matter how many times you flip the coin, like the next time is always independent from all previous time and also what you get afterward. So that's what they call independent. So all you do here is just you multiply bunch of probabilities together. So that's all you do for calculating the likelihood for sequential events. And of course, if you like multiply bunch of probability which are between 0 and 1, you will get like extremely small numbers if you have like too many, right? So let's say, yeah, you have like n data points, then you get like extremely small number as n becomes large. So what we do here is we take the log likelihood because hopefully you remembers the log of product, you can convert it into a summation term, right? So now we converted a multiplication of multiple small numbers into a summation term. So we have like a better numerical value to work with. So it won't get it to be extremely small as n grows. Right. And then log is also, as you know, monotonically increasing. So it's like always increasing from 0 to infinity, right? I mean, it's undefined at 0, but like to the right of 0 to infinity, it's always monotonically increasing. So here you can just reformulate this objective here of MLE to be a log likelihood. That's what we call the log likelihood. Yeah, so, and you know your probability is always between 0 and 1, right? So the log value of that is always negative, but we are summing over all the negative terms. You try to make this term as close to 0 as possible, right? Right, because you're trying to make the probability equal to 1, basically. So in here, you want this term to be maximized, right? Which is, yeah.
If we maximize this, it's the same thing that if we maximize the log of it.
Yeah.
And the
So
log of it is just the sum of the log of each data.
yeah. So basically all we do here is we have the same, like we're having the same objective. So you're trying to achieve the same thing. But instead of doing multiplication, which is very hard to work with when you have like a very, very small number, here we turn it into a summation term. So it's easier to get. But the objective is the same. And then maximizing maximizing this term, like the summation term here, is the same as maximizing this thing here. So it's the same thing, it's just different like mathematical formulation for easier purposes. Yeah, so the objective is the same. So if I tell you you've seen maximum likelihood before in MLF, does anyone know where you've seen it? Like potentially?
The loss. Loss function.
Yeah, so it's a loss function. Yeah, so in fact, everything you've seen, so all the models, probably except decision tree you've seen so far, you're actually implicitly doing a maximum likelihood estimation, but without knowing it. So yeah, MLE is pretty much everywhere without you probably being noticed about it, but now you know. So let's say just the case for a linear regression model, right? So you say the data, let's say you have like a trained model, and then your models just say, oh, I believe this data is being generated yi equals to wx, right? That's what you kind of learn. So for now, just ignores the epsilon term in the end. So that's what make a model deterministic, right? Because your weight of W is fixed after training, and then you have some sort of input X, then no matter how many times you gave the same input to the model, it will always produce the same Y, right? Ignoring this term, like ignoring the last term. Then it's just deterministic, right? That's what you kind of learn in the first week, I think. And now let's say for probabilistic model, however, let's add some sort of noise to it, which is given by a noise term here, epsilon, with an mean of being 0 and standard deviation of sigma. So all you says here that is because you know your data is not perfectly linear, right? So it's not like just if you see the diagram, it's just not all lining on the blue line. So no, you know there's some sort of error or whatever you call noise or error within the data. So your model kind of account into that, right? So you know there's like uncertainty. Like if I gives you like an X value of 0, if you have a deterministic model, it will always produce a point here, right? Like exactly. But your model knows that's not always the case for the data because there's some fluctuation or error within it. So it tried to maintain the distribution of how likely or how big the error could be. That's what this term does. So every time in this case, your epsilon of I will be something slightly different, right? It will be a small fluctuation, but it will be something different. So if you give the same X, sometimes your model will give like a prediction here, and then sometimes it may give you like a prediction here. So yeah, it's fluctuating. So what it means is that if I gives you the same input, now you will get roughly the same output, but not exactly the same as before. And this model understanding, you can just be considered as a model as a Gaussian random variable. So given your X, which is your input, and W, which is your weight, right? So you know, so basically that's your deterministic part. So your input is fixed, and then your model's weight is also fixed, right? So now you're trying to predict how likely or predict the probability of your output being something like exact number. And all it does here, as you can see on the diagram, is just some sort of distribution, like Gaussian distribution in this case, centered around whatever this term is. So W times X is your mean value because you know that's where the data is most likely to be equal at, right? But there's some sort of noise, so that's why you have like a variance or standard deviation around it. So now instead of predicting exactly on the line, you're kind of predicting data surrounding the line as well, if that makes sense. Does it make sense? No? Yeah. Can you tell me where you don't understand? Or anyone else?
What is
Hmm?
this curves.
This curves. This is just a probability distribution.
But how do you interpret?
So basically, let's say for this one, right? So
Probabilities 0.5.
sort of, yeah. But that's your y value, right? So let's say given x equals to 0, right? Let's ignore the epsilon term. Like, let's ignore this. Let's ignore everything like on the diagram here. Let's just see the blue line. Then it gives you a fixed prediction, like kind of around y equals to 2.5 or something, right? So that's always deterministic. But now your data is not always 100% on the same line, right? So you're trying to add some sort of distribution. So this curve just says it has the highest probability of being here, like being exactly to be 2.5, but also has some slight chance of being higher than 2.5 or lower than 2.5. So it's a range instead of being a point.
You apply this function only at the -2, 0, and 2.
No, it applies everywhere because given any x, you are still. Oh yeah, this one's just like a demonstration at this point. But on the curve, like every single point on the curve, you will see something like this. There are infinite many of them. Right? Because you have like one here, then you can have like one at any single point of the graph. Okay. But all it says here is that your model knows the mean of the prediction, the mean value of the prediction will be somewhere centered around 2.5. But there's some like plus or minus around it. So that's all like what the model learns. So instead of being deterministic, it learns to be a bit, right? Like it has some sort of fluctuation around. Yeah. So yeah. So now this is right. So this is what the distribution of your model learns. So given your model here, which is defined by W, and also x of I, which is your input, then your distribution is just about your prediction of y of I, right? So now let's do the likelihood term. So let's say you have n data points. You can say it's like n coin flip or something. Actually, it's probably not coin flip, but let's just say like you have n different house prices or something. Then you assume each data point is independent from each other, right? And then you're trying to build a model that best fits all the data points, not just a single one, right? So that's why you multiply all of these together. And then that's how you like the likelihood, because we assume all the data points are independent from each other, right? So this is your likelihood term of W. And we take the log of it, as we said before, because we don't want like multiplying lots of probabilities together to be small. And so this is a term you get. Do you guys see this term being, well, here it's just like the first term is just a constant, right? Because it's just like n pi and then sigma, so those are all constant terms, so you can just ignore this, right? But does this term looks familiar to anyone? Like the second term? Yeah, so this is exactly your mean square error loss when you're training your linear regression model, right? So you can see here that we're converting a linear regression model also into some sort of also convert it into a maximum likelihood estimation, because here what you want to do is you want to maximize the log likelihood, right? So the idea here is that when you're training the linear regression model, you're minimizing your mean square error loss, right, in this term, which is this term. And here for maximum likelihood or maximum log likelihood, all you do is you're trying to maximize this term. Because, well, there's like a negative sign here. So minimizing this without the negative equals to maximizing this with the negative, right? So the objective is the same. So when you're training your linear regression model, all you're doing is also, you can think of it as maximizing the likelihood. And this applies to the case of linear regression. Then it also applies to lots of different machine learning models, like logistic regression, neural network. Those are things you've seen before. And also different kinds of generated models you're probably not familiar with, like GANs or VAEs, but those all have very similar objectives to MLE. But those models are not considered to be somewhat truly probabilistic because they do not treat, like, remember our definition, CERT definition for a true probabilistic model is that you treat each parameter as a random variable, which is like your parameter is not a fixed value. But for so far, we've seen all the parameters we still consider as fixed, right? And then we'll see what that like true probabilistic model means in the last section of this. But for now, just like these are not, you can call them probabilistic models, but they're not. Okay, they're probably not probabilistic models actually. Yeah. And limitation of MLE. So maximizing MLE objective does not make a model truly probabilistic as you've seen so far, right? Well, as I said, because it doesn't treat your parameters as random variable. And also MLE sometimes will be overconfident when the data is insufficient, or it ignores the prior, which is what's coming up next. So if you don't know what's a prior, that's fine. But it just knows that MLE only makes prediction based on what it sees so far. So it only sees like a very small sample of data, then it's probably kind of like overconfident on what is actually going on, because there might be like luck or whatever, right? Or just coincidence. Yeah, so as an example, let's say if you see a coin flip of head and head, then your MLE, you're just trying to give the model that best generates this data, right? And then of course, the best model is just to have, let's say I have a coin that always lands on head. Then it gives me 100% chance of always observing two heads when I flip the coin, right? But you know that's probably not the case because there's probably not a coin that always lands on head on this planet at least, right? So that's what we call the overconfidence of MLE. Yeah. Yeah. Do you have questions for this section? No? Okay. So now let's talk about discriminative and generative models. So let's just step back a little bit and then talk about classification problem as a recap. So for classification problem, it's just you have some sort of data points, right? You have multiple of those, which can be described by features, right? And then you have set of possible classes, so which is what your prediction could be. And you just try to determine which data point belongs to which class, right? That's what you've seen before for logistic regression, which is binary classification. So in that case, you only have two classes, but you can have more, of course. So discriminative approach means that, well, I know there are two classes, right? Then all I need to do is I just try to figure out where those two classes separates from each other, right? So I try to draw a line that distinguish the two classes. Let's say like I draw a vertical line, and then if it's on the left of the line, then it probably belongs to class 1, and then right, if it's on the right of the line, then it probably belongs to class 2. So something like that. That's all what you did for logistic regression, right? Or even neural network is doing the same thing. But for generative approach, it says the model first tries to distribute. The model tries to kind of create some sort of model that sees or that kind of construct the underlying distribution of all the possible classes. So instead of saying what a line looks like, the model first tries to understand what each class looks like. So let's just see an example here. So here you have like two set of data, right? Blue and red. And for deterministic, you just care about the line, right? You care where is the boundary. So where are the data being separated, right? So this middle line is all you cares about. And you can distinguish which class it belongs to just by seeing where the point is in this case, right? So if it's to the like bottom left of the line, then it's probably blue, and then if it's to the top right of the line, then it's probably red. So, but the model has no idea of what the data, like what those dots actually looks like, right? So generative approach, however, it doesn't care about where the data being separated. So first think of the data as some sort of distribution or cluster you can think of. So here, what your model do for generative approach is it tries to understand what the data looks like for different classes. So just in this case, what it constructs is it says, oh, the blue points is something, it's kind of like more circular shape, right? Centered around probably this point. So this is like the entire blue region is a distribution, right? So it tries to understand where this data points lives in the space. And similar for the red one, it means it lives in a different region of the same space, and then it's more like an oval-like shape, right? So instead of being the line, your model knows more because it knows what each class looks like, right? Yeah.
Does it give like a probability, like if you are near the end of the circle?
Yeah, so
less probability
yeah.
than the center.
Yeah, so it depends on the data point, but in this case, you can think of it like this is a 2D thing, but you can imagine it's like being a 3D. So it's kind of like cone shape. For this case, like if you're at this point, it probably has a higher probability within being a blue data instead of like than here, right? Because here basically you don't see any data so far. But yeah, it's just like at this point, you can say it's more likely to be blue than red, right? But you're not 100% sure that this is blue anymore. But for discriminative approach, you don't care. You just say it's to the left of the line, this is 100% blue, right? So you see there's some sort of uncertainty or probability involved there. Yeah. And generative models are usually done in 2 steps. So what it does is first it builds internal model for each class, which is what you see here. And then once you have this internal model, you can do whatever you want with it, right? Because I give you a point, you can also make prediction, or you can also sort of generate some new data, right? So you can generate a data here that has a small chance of being blue, which you cannot do with the discriminative model because you don't know, right? So like what you can basically generative models knows a lot more than the deterministic model. Because all actually, am I using the wrong term? Discriminative models. So discriminative models, all it knows is where the line lies, right? So only just try to separate 2 things. But generative tries to understand what each class actually looks like. So it knows a lot more. So here's an example, right? Let's say I give you animal and some sort of its feature like weight, size, color, etc. Right? And then you're trying to predict whether given this feature is the animal or a cat or not. Right. So for discriminative approach, it's just 1 step, right? So given you're training a model, given all these features, and then you're just output 0 or 1, or like a probability is cat or not, right? So pretty intuitive. It's just a classification problem. And it's a direct mapping. For a generated model, you're doing 2 steps. So your model is trying to first understand that given a cat, what kind of weight, size, or color would it kind of have, right? So you can see the weight, size, color given a cat is not exactly fixed, but it's within some reasonable range, right? So your models first try to construct some sort of understanding of what a cat's weight and size and color could be. And then once you have that understanding, then you can say, oh, you can even generate a new cat data, which is like, you can say the cat probably weighs like 5 kilograms, right? With like color of black or something like that. So you see generative model is more robust, or it has like a better understanding of what each class looks like than discriminative models. And then next you do is just you do inference because you already have like a understanding of what a cat look like, then it gives you any sort of feature, you can predict whether it's a cat or not. And that's the easy part, right? And it's done through Bayes rule, which we'll see in the next section. Does that make sense for this section? Okay.
Are we going to see how it constructs the internal model?
Yeah, next section. Yeah, so now let's talk about Bayesian model. So first, let's introduce some terminology. So prior, which is what we kind of introduced, well, we mentioned before. Now let's formally introduce it. So let's say if you see the following data of a coin flip, you just see 2 heads row. So you see many coins, right? You know this is not, it's likely just be like luck or like coincidence, right? Because you know there's probably not a coin. Like based on what you see so far, the best bet you have a coin to see this data is a coin always lands 100% on the head, right? But you know that's probably not true. So your knowledge of a coin, let's say being most coin in this row being fair, or being biased, but not 100% like always lands on head is what we call prior. So it's your knowledge of the event before even seeing the data. So like I ask you what a coin could be, you probably say it's most likely to be fair, right? That's your prior, because I haven't given you any data, and then you just, based on all the coins you've seen so far, you think it's most likely to be a fair coin.
Just for initializing the model.
Kind of like you're injecting an initial knowledge to your model, right? So because in this case, if you train an MLE to maximize the chance, your model would just say the best model for this data is that a coin is landing 100% on head, right? But based on your real world knowledge, that's probably not true. So you're trying to inject some previous knowledge into the model, saying that, oh, most of the coins on the world are fair, right? And then some of them are biased, but probably not. None of them are like landing on head with 100% certainty. So you're trying to inject some prior knowledge to the model. And then we define this term as the P of theta. It's just your belief or assumption before even seeing the data. So that's what you know beforehand. Okay. And posterior. So posterior means that, okay, you flip the coin a few more times. You observed head, head, tail, head, head as your sequence of data. And you realize your prior model of coin being fair might not be too correct anymore, right? Because it still has a chance of not being a fair coin, and then you just get like unlucky, you land on heads a lot more time than tails. But you could probably kind of suspect that the coin might be biased, and it has a higher probability of landing on heads than tail, right? So this means that once you observe more data, you have a sort of better understanding of what this coin could be, right? So for posterior here, given by theta given d is your data, theta is your model. So your posterior is just your updated belief after seeing some sort of data. So your prior is before seeing the data, and then posterior is your internal model, or the model, like what a coin could be, after seeing some sort of flips, right? So you have more knowledge of this coin, basically. And so here's base rule, right? So you have prior and likelihood, which is what we introduced before. Hopefully you still remember what it is. Evidence, we'll talk about in the next part. And then your goal is to compute the posterior, right? So here, the likelihood term is your internal model that you constructed through MLE, as you've seen before. And then the goal is that, okay, I know some sort of like let's say just in this case, what a coin could be beforehand. And I flip it a few times, so I get a better understanding of what it could be, right? And then my posterior is just my updated belief of the coin. So as an example, you just say your prior is that you know the coin should be fair, right? So that's your prior. And then after seeing, let's say this data, you suspect the coin is more biased towards head. Then let's say your posterior in this case is this coin that lands like 70% on heads and then 30% on tail. So you're updating your model, right? You're updating what the coin could be.
Like here is the product of.
Yeah, it's just
small b.
Yeah, it's just what you've seen before. It's the same thing. Like exact same as like this. Similar to this, not exactly, but because it's a different problem formulation. But okay, so now let's talk about evidence. So just remember, evidence is on the denominator of your equation. And evidence tells how likely each observed data are. And this it's averaged over all possible parameters or all possible model values that you have. And they can be computed with probability, total probability. And for this discrete case, you just make summation. And for a continuous case, you use integration. But this doesn't matter too much. And evidence in real life is really very hard to compute, which we'll see like an example later. But usually we just know that we use some sort of estimation for this term. So for the bottom part, and all it does is just try to make the probability sums to 1. So you can think of it's more like a numerical term that doesn't matter too much for downstream like tasks. But let's just do an example right now. So for like better understanding. So let's say you have 3 coins, A, B, and C. Coin A is fair. So like 50% lands on head and 50% lands on tail, right? Coin B is biased. It has a 70% chance of landing on heads. And then 30% chance lands on tail. And then coin C is the opposite of that. So it's less likely to land on heads than tail, right? And then you pick a coin randomly. So you flip the coin twice, and then you observe 2 heads as outcome in a row. And you want to know what's the chance of observing another heads in the next flip. Okay. Is this problem clear to everyone? Yeah, hopefully it's easy. So here, yeah. Oh, here for prior, you just assume the coins pick at random, right? So that's pretty intuitive. And for likelihood, it's just the chance of seeing 2 heads in a row given any of the coin it could be, right? So that's your likelihood, which is what we talked about before. And for evidence, it's just the total probability of observing heads given all the possible scenarios, right? So let's just do some computation then. For prior, it's easy, right? Because you know the coins are picked are uniformly random, so each coin has 1/3 chance of being picked in this case, right? And your likelihood for each coin, which is your internal model, so you know if you picked coin A, the chance of observing 2 heads is just 0.5 times 0.5, right? Because 2 flips are independent. So you know the total probability of seeing 2 heads given A is 0.25. And you do similar things for coin B and coin C, right? So you now have a likelihood term for each coin, right? And that's what you call internal model, because once you pick a model, you know how likely would it generate the observed data, right? And for evidence is that it means that you want to see the all possible scenario where you can get 2 heads in a row. So you need to consider the case for all 3 coins, right? So a coin can be A, B, or C, and then all you're doing is just you're summing all their possibility of giving this data together. So I actually didn't compute this term, but this is the total chance of, like overall, the chance of you seeing 2 heads, no matter which coin you picked. It's just the total or the overall probability of you getting 2 heads when you flip a coin twice. And then you don't know which coin is being flipped, but that's just your evidence. And for posterior, which is your inference step, so what you're doing is that you're trying to understand how likely you're holding each coin, right? So before, your understanding is just that each coin, like you're equally likely with 1/3 chance holding each coin because you don't know anything about what you're holding, right? So you just assume they're picked at random. But after seeing some sort of data, you can say, oh, I have like a better understanding of what the coin could be, right? So like here, you're just applying the Bayes rule. And here is what you get as a probability. So here you say, oh, after seeing flipping 2 heads, I suspect the coin I'm holding is more likely to land on head than tail. So after updating my belief, I believe I have like higher chance, which is close to 0.6 chance, holding coin B, which is the coin that's more likely to land on head, right? And then I have some chance of holding A, right? Because it's fair, so it's totally reasonable. I see 2 heads in 2 flips because they still have like 1/4 of chance seeing that, right? And then for coin C, which is more biased towards the tail, so it lands on tail more often than head. You know, if you observe 2 heads, the chance of you're holding coin C is quite small, right? It's relatively unlikely, although it's not impossible. So yeah, that's how you apply Bayes rule to compute how likely you're holding each coin. And once you have that, as I said, you can do anything with it, right? You can calculate the chance of getting a next flip in heads because you know for coin A, this is the chance of you holding coin A, and then coin A has 0.5 chance of landing on head, and then do similar for coin B and do similar for coin C. And then you see that you have 0.5596 chance of getting a head in the next flip. Because based on what you observe, you suspect the coin might land on head more often than tails, right? So that's why you're observing the next head will have like a higher probability probably higher than 50%. Yeah, does that make sense? So yeah, here's the takeaway. So before seeing the data, before seeing 2 head flips in a row, you believe all 3 coins are picked randomly. So they have like equal probability of being picked, and you don't know which one you're holding, right? And after seeing 2 flips, you realize the coin is just more likely to land on head than tails. So, right, and that's like not really 100% sure. You're not 100% sure, but based on what you see so far, at least that's more reasonable case, right? So after seeing the data, you change your belief, and it becomes just the coin I'm holding is more likely to land on head than tails. So here it just says I'm most likely to probably holding coin B, and then coin A, and then least likely holding coin C, right? What prediction would M of E gives you? I kind of gives the answer away already, but does anyone know? For the bottom question, I kind of give the answer twice already. So, like if you're observing head and head, what MLE would give you?
B.
Yeah.
Probability.
In general, yeah, it will just gives you like whatever maximize it, right? It just gives you this 100% B. So that's yeah. Okay, so far the Bayesian rule we talk about, or Bayes rule we talk about, is something called naive Bayes. So it's naive because we assume the features are conditional independent given the class. So just as formulated as the coin flip problem we had. So it says that given a coin is biased, or whether it's biased or not, doesn't matter. Each flip's outcome is independent from all its previous flip and the other flips afterwards, right? So the first time you flip, it doesn't matter what you get. Your second flip is independent of that. So that's what we called conditionally independent of the feature given a class. So yeah, and this condition is true for the coin flip example, as you might imagine, but generally it's not always true in the real world scenario, right? Because so that's why we call it naive, because it's just a naive assumption, and then you'll see where this assumption breaks soon in the next example. But nonetheless, it's a good enough estimation for our purposes for now, right? Okay. Yeah, so any example, or no, any questions so far? Okay, good. So now let's do a more interesting example, which is spam classification. So suppose you have an email, which is built out from some sort of vocabulary of size D. So you have D different words you can use, right? And we represent this email just as a binary feature. So just see the image here. So let's say you have an email that use the words then you just put 1 there. And then if the email doesn't contain the words car, you put a 0, right? And then if it has a words car, you put a 1. So you can construct some sort of, this is your feature vector X, right? And then you can construct some sort of feature vector for each email. Does this make sense? It just counts like which words appears in the email or not, right? So it's just binary 0 or 1. So 1 means it's present, and then 0 means the words is not in the email. And then let's just assume for now, like the amount of words is fixed. So you have like, let's say you have like 100 words to use from, right? Yeah, and then for your class, it's just binary, right? So it can be either 0 or 1. 0 means your email is not spam, and then 1 means your email is spam. And data set, just imagine you have some sort of emails, like a bunch of emails, and then whether they are spam or not, so they're labels, right? And then your goal is that given the new email, is the email spam or not? Okay, does everyone understands how the problem is constructed? Okay. Yeah, so now we can construct some sort of joint distribution. So joint distribution just assigns a probability to all possible scenarios. Like we're basically can think of it as all combinations of the possibility given all the features you have. So let's say, for my case, I can have an email being spam and just contains a word of one word of that's one possible scenario of what it could look like, right? So ideally, your model would assign a probability to that thing, right? But you know it's very unlikely, but ideally your model still gives like a very small probability. And that applies to every single possible combination of the words in our case. So totally, you will get like 2 to the power of d plus 1 number of parameters, right? So you're keeping a distribution, we're keeping a probability distribution for all those cases, right? Because you have d words and then one class. So that's d plus 1 term. And then you're just trying to calculate all possible scenarios. In this case, there are like 2 to the power of d plus 1 possible scenarios. And let's say if you have like only 100 words, which is d equals 100, then you have like total of 2 to the power of 101 scenarios, which is already way too much to compute, right? So this is really unrealistic to compute. So what we need to do is that we need to reduce the problem size dimension. And how are we doing this? Is we're using the naive Bayes assumption. So we assume that each feature here is conditionally independent from each other. So now we can consider, now we can convert this formula into a product of bunch of probability. So here, what we're doing is just that instead of treating every possible data point, like as we're treating all the combination of all possible words and class together, each as a separate parameter, we only treat each word as an individual parameter. So instead of all possible combination, we reduce the probability dimension to 2d plus 1 because you have d parameter, which is d words, right? So how likely a word appears, whether in a spam email or not. So for spam, you have you're tracking d parameters, right? And then for non-spam, you're also tracking d parameters. So there's total 2d parameters. And then for the plus 1, it's just you have a prior to track as well. So there's total 2d plus 1 parameter you're tracking. So that's a lot smaller than what we had, which is in this term, right? So of course, if we use the naive Bayes assumption, we're losing some sort of information here. And then in this case, as I said, naive Bayes assumption is true for the coin flip example, but it's not true for this case because in this case, we treat words independent from each other. So it means what words comes before or after in the email, it doesn't matter to what words you have. And that's definitely not true for language, right? Because you know, like some words are likely to appear together and some words are not likely to appear together. But in this case, we ignore all those effects. So that's where we lose information from this assumption. Okay. So, well, for this case, for spam classification, right? So you're trying to understand the prior, and your prior is hopefully simple. It's just how likely your email being spam or not spam, right? And then here I just denote it as P of C, and C is just your class. It can be 0 or 1, which stands for spam or not spam. So your prior is just how likely an email, like given, is spam or not spam, based on your previous understanding, whatever, right? And then the likelihood here is that given an email is spam or not spam. So here's important. You need to first know the class, whether it's spam or not spam. And then you want to see how likely a given word is present in the email or not. Prior, we'll see later. We'll do a numerical. Yeah, we'll do numerical later. But yeah, for now, you can just think of it like based on your total observation or whatever, right? How likely would the email be spam or not spam? Right.
spam already overload.
Yeah, so like that's exactly what we're doing in the next slide. But we'll see later. Yeah. And then for the likelihood, it's just that given an email, spam or not spam. So knowing the class is important because you're trying to keep track of a different separate distribution for each scenario. So let's say I say the word win, right? So given the class being non-spam, the chance of using the word win in the non-spam email is probably low, right? So but in a spam email, you see the word win is probably very high, right? So you're trying to keep track of the separate distribution for each. So basically for each word, you have, in this case, you're tracking two distribution, one for spam case, one for non-spam case. That makes sense. So after having the prior or likelihood, we can start training. So training here is just means we get a more accurate estimation of the distribution based on the data we have, right? And the good news here is that in naive-based training, there's no gradient descent or anything like that. It's just purely statistical method. So let's say for prior, right? You have a data set. You have total n numbers of emails, and then you know like NFC of them are spam. So if that's all you have, then your knowledge to the best extent is just say that I know what percentage ratio of my data set is spam or not spam. So your prior just based on that, right? So it's like number of spam divided by the total number of emails you have. So that's pretty intuitive. And of course, the more data you have, the more accurate this prior is, right? And then we can also estimate the likelihood. So likelihood is that given the number of training emails with class C, which is there are two types. So it can be all the training emails being spam or all the training emails being non-spam, right? So there are two classes. So you have two types. And then for n of j of c, you're just it's just the number of email where you have the word appears in it, right? So, and then it's also statistics. So you just try to devise this. So how you compute the likelihood of a word appears in a spam or non-spam email is just you count the total number of spam or non-spam email, right? And then you count how like the total number of words appears in a spam email or not, and then you just divide that. So this you can also use MLE to do this, and then you'll realize if you do MLE, you do a like log likelihood estimation. This term is exactly what you get. So for simplicity reason, we just give all the messy mass, but this is also like maximizing the likelihood. So it's the same thing what we're doing before when we computing the log and then when we multiply the probabilities together and then maximizing the log, and then you will realize this is what you get. So I just skip all the intermediate step because it's kind of confusing. But nonetheless, it's just purely statistical method, right? And then you do this term for 2D times for each class. And then you can calculate the likelihood word for each word given that class. So basically, I give you a word. After training, you can tell me how likely, let's say, I gives you let's say the email spam, right? Then I gives you the word win. You can kind of tell me how likely would that word appears in a spam email, which is probably high, right? And if I tell you I give you a non-spam email, how likely would the word win appears in it is probably a bit lower than, right? Where it's just not common at all. So now you have the prior and the likelihood. Then what you can do is just you can compute the posterior basically. So yeah, so here's not posterior. It's just like you can compute a likelihood for each email given the class. Because so far here we just treated each word separately, right? But email contains a bunch of words. So what we do is in simple, because due to the naive Bayes assumption, we can just multiply all of them together, right? So that's like X. X is like an email with many different words. And then given a class, you just try to predict that given here, like let's say given an email is spam, how likely would it see all those words combined together, right? Like how likely would it be? to see this email if it's spam. And here it's the same thing, just for non-spam. So it's the same, but different class. And then once you have the likelihood, so here's the likelihood for each individual words. And then here's the likelihood for the entire email, right? And then once you know the entire likelihood for the email, you can just apply posterior. You can just compute posterior, right? So given some sort of new email, whatever it could be, you can compute whether it's spam or not spam. And this term is, in the end, is your prediction, how likely your email is spam or not spam. And as we talked before, the bottom term is evidence, right? In this case, it's pretty easy to compute because there's only two cases. But for like, let's say we have like lots of classes, or infinite many of classes, then the bottom term would be impossible to compute. But in this case, it doesn't matter because you see the denominator is the same, right? Or they're the same. So you only cares about numerator, and you only pick the higher numerator to be your prediction in this case. So that's why the denominator doesn't matter. Yeah. So does that make sense? Yeah. So here's the takeaway. So the training for Bayesian model, it tells you two things. So first is how often the emails are spam or not spam, and that's required, right? And the second thing is that if the email is spam, how often would each word in the vocabulary appears in it, right? So because you know some words are more likely to appear only in spam email, and some are only likely to appear in non-spam email. And so you're trying to figure out that likelihood, right? So that's for training. And for inference, you're trying to estimate the likelihood of the new data you're given. So if you're to generate a spam or new spam email, right, how likely will you get the given combination of words? So that's the first thing you figure out. So you try to figure out how likely would those combination of words appears given I'm trying to generate spam or non-spam email. And then the second term is just incorporate prior. And then you can apply Bayes rule because, well, in this case, both the likelihood and the prior are useful to your prediction, right? Because likelihood was what you see from the data, and then prior is what you learned before, like before training. So you try to utilize both terms to compute this.
How do you train the model? Because we saw that it's only one step, and in one step.
This is the training step. Like it's
Just compute this.
yeah, it's a statistical training. As I said, there's no gradient descent or anything here. Your model is purely statistical in this
One
case.
step. Yeah, okay.
So basically, like you can imagine you're just doing counting for this case,
Yeah.
right? Because there's no like gradient descent or whatever. Because all you have is just the data, and then you're trying to compute this.
Exterior is the inference.
Yeah. So pros and cons of Bayesian models. So Bayesian models, as you see, it's very cheap at training time, right? Because it's just basically counting, and there's no gradient descent. You don't have to do like so many epochs over. So it's pretty easy. Yeah, and then for test time, it's also easy, right? You don't have to let your input flow through a bunch of layers to get an output. You just need to apply Bayes rule, which is like 3 multiplication or like division, which is very easy. However, Bayesian model are generally less accurate than discriminated model just due to its like assumption of the input are being independent in this case, right? Because let's say for our example, how each word appears. There should be some correlation between what comes in front and what comes after, which is what we call context in general, right? But in this case, we just ignore that completely. So that's like a limitation of naive Bayes model. Okay. So yeah, that's it for the presentation. Does anyone have any questions regarding this? Otherwise, I can move on to PyTorch. Hello?
What are the application? When it would be used.
It's mainly used in like, honestly, I don't see too much like use cases, just because that the fact that lots of it can be done by neural network or stuff, which are more powerful. But it's really if you need, like you have very large amount of data and then you want like very cheap model, whereas like a Bayesian model is a very good and then fast way as a benchmark to see what's in, like you can just, because training neural network, like if you have like very large data is very difficult, right? And it takes lots of money. So you just want to see like as a simple benchmark, this is a very good choice to do. Because it's cheap and it's like easy to do compared to like, and it like training is very quick, right? Okay. Okay, so let's just do some coding then. Should be big enough, right? Okay. Okay. All right, so first we can just do some probability warm-ups. I think those are pretty easy because it tells you the formula already. So, right, for joint, you just do return P of A times P of B, right? Because that's a formula for joint. And for a conditional, it's also similar. It's just P of AB divided by P of B, right? But for this case, you have to assume P of B is non-zero. But nonetheless, they kind of give you the formula here, so it's pretty easy. It's just return P of AB divided by P of B. Okay. And similarly for base, you just use the formula, which is P of A given B just equals to P of B given A times P of A divided by P of B, right? And for this case, you also assume that P of B is non-zero, of course. Okay. Yeah, so hopefully that's pretty intuitive. Yeah, there's a formula already there. So you do nothing, just convert into Python syntax. So yeah. So now let's do some Bayes as generative models. So let's say we just have a data set here of some being spam or non-spam. So this is a very small data set. So we have like 14 examples. So here the label 0 just means the email is not spam. So it says, actually this is not really email, but just some sort of text. You can think of it as email, whatever. So it's like, hey, are we still having lunch tomorrow? This is probably not a spam email, right? And let's say if you say win cash for free price, that's probably a spam email. So it's just like you have your 14 different data and then with their corresponding label. So in this case, the data set is balanced. So you have like 7 non-spam and then 7 spam, but it's like a relative, very small data set. And so now we just built the vocabulary from it, right? So vocabulary you just see that the vocabulary can contain the words the, claim, for, win, you, right? Like all those kind of words. And then we just build it as a vocabulary as what we see here, right? So that's like kind of just how we're dealing with like as in this image. This is how we convert a vocabulary into a vector. And then the vector size in this case is 69. So it's just one entry for each word. Oh, you just use the function. They have like a built-in vocab function for you.
Which library? Which library?
I don't know which library is this from. Oh, is it in util file? Okay. Oh yeah, they built it for you, so. Like someone else implemented for you, so it's in util.py. But you can, I mean, it's like just a simple count, right? Like you count each words, how many times it appears. And if it appears, you just give it as 1. And if it doesn't, just give it a 0. Right, so it's pretty intuitive. We're not gonna go through it, but you can. Yeah, it's like inside util.py, so if you're interested, you can go back and look at it. But I'll just convert it into a vector. Yeah, like it's converted like let's say raw text into a vector, like 0, 1, right? So, oh, no. So like here what you have is like just pure words, and then you're trying to convert into like a vector of 0, 1, right? So that's just basically all you do. Yeah, basically convert like a text into numbers, right?
The vector has the size of your vocabulary.
Yeah, like in this case, like 6 or 9, because our data set is very small. So yeah, like in this case, you have like a vocabulary size 6 here, right? So yeah, like here 69, right? Okay, so for fitting the classifier, I guess I'll give everyone like maybe 5 minutes to think of it, like how you do it. You don't have to do the exact probably syntax correct, but you just like have a general idea of like how you do it. And then we'll come back and go through it together. Okay, yeah, so yes, let's just get back and then quickly go through the code. Here there's lots of print statements, so just for visualization purposes, so that's why it looks kind of long. But let's just walk through what's happening here. So first, we just have built vocab, right? So that was the same thing as before. And then we also do vectorized, so just 0, 1. And number of features is the length of the vector, right? So here what we're doing is just we're trying to split the model into like a training set and a test set. Although the data set is very small, but we still do that. And here we actually indeed we just use like a built-in model, and then we can just use it for convenient purposes. And then the mode is Bernoulli. It just means 0 or 1, so it's binary. And all you do is pretty similar to what you do before, and then you just fit your data into the model. And these are all for printing purposes, so it's not important. And in the end, you just do a prediction on the test set, right? And then the test accuracy. So let's just see what this gives you. So yeah, like it just print out some statistics based on this. You have your prior, right? So your prior of the email being non-spam is like 0.58, and then chance of being a spam email is like 0.41, right? And then you have a likelihood for the samples for each word. So some words are more likely to appear in a spam email, some are not, right? So like let's say when it has like a 0.1 chance of just appearing in a non-spam email. And then for the spam case, it has a chance of 0.5. So it's a lot higher to appear in the email is in the spam email. Yeah. And then surprisingly, the test accuracy is pretty high. I think it's just due to our data set is very small. There's only like 14 examples. So yeah.
How do you test accuracy?
Oh, you just do predictions, the same thing. Like it's pretty much like here, it's pretty much similar to what you did with all your previous models before. Like they will handle like lots of stuff for you, so you don't have to worry about the like how exactly it is implemented in this case. Although if you're interested, you can look into it, of course. Yeah, so now let's say this is a SAM text I built, use the vocabulary. I built with the word within the vocabulary. Apparently this looks like a spam, right? And this is not within the data set, so let's just see. With the model we trained, right, it will predict this one being spam. So with a chance of 0.84. So apparently this looks like a spam email anyways, right? Smoothing, we are not going to talk about. But for smoothing, it's just that there's some sort of alpha parameter you can tune with, and then we'll deal with the case where the words does not appear in the email. But because we didn't cover this in the presentation, so we're not talking about this because it requires some background knowledge. But if you're interested, we do have the solution. So, and they will have, wait, not this one. Wait, cadence the solution up. Is the solution up?
Where this.
Yeah.
Oh yeah. It's just on the page.
Oh, okay, then yeah, you can find the solution for implementing the smoothing in on GitHub, and then you can kind of go through it. But yeah, this is not where we're gonna cover. So, and you can also just, I mean, we kind of answered this already, so you can just do it as an exercise going back home. Yeah, so that's pretty much it for this week then. Yeah, so I guess we can end early then.